To begin our study of electric fields in the static condition, we're going to start with a very simple situation, and that is the electrostatic condition that exists between the interaction between two stationary charged particles. And so by this I mean what happens if we have two protons that are near each other in space, or what happens if we have two electrons that are near each other in space, or what if we have a single electron or a single proton. And we're going to do it for two particles. You could extend this analysis for an infinite number of particles. We'll show the techniques to do that as well. But to analyze the situation of two interacting charged particles, we got to discuss this idea of charge. And we use it a lot, but what do we really mean by saying something has charge? And a long time ago, it was observed that some objects, some materials, or as we now call it matter, would either attract or would repel other matter. And it was noticed that this property of attraction or repulsion could be developed in materials that didn't otherwise have this property. For example, you could take a piece of amber and place it next to pieces of torn up paper, and nothing would happen. But if you take that exact same piece of amber, and then take a piece of silk cloth and you rub the amber somewhat vigorously with the silk cloth, and then you put that piece of amber next to some small torn up pieces of paper, all of a sudden the amber is going to attract that paper, and the little pieces of paper are going to stick to that piece of amber. And so somehow we were able to give the amber the property that it could attract these pieces of paper to it. So we were able to imbue this amber with this property. And this was kind of the first observation of what we now know to be electric fields. And through a lot of clever experimentation, it was eventually determined that if we look closely enough at a subatomic level, all matter is composed of what we now know are these tiny particles called electrons and protons. And there's neutrons in there too, but we're not concerned about those because they don't they don't carry charge. They're neutral. So anyway, these electrons and protons, these charge-carrying particles that make up a ball of matter, they always are exerting forces on one another. If the forces are the same type, the particles repel each other. So if we have two protons, we know that these protons push away from one another. And if we have two electrons, we know that these electrons push away from one another. However, if one of the charges is positively charged and the other one is negatively charged, then they're going to attract. So if we've got a proton, for example, and an electron, those particles are going to get pulled in towards one another. And what you should note about this is that the terms positive and negative in this kind of intellectual formulation, they're completely arbitrary. We could have called it type A and type B charge. We could have called it red charge and blue charge, but we don't. We call them positive charge and negative charge, and really we just inherited positive and negative as descriptors of this fundamental property of matter that can either cause attraction or repulsion. Like, there's nothing special about positive and negative. So charge, it turns out, is just a description of a property of particles of matter, just like mass or length is a description of a property of matter. It just happens to be that there's two types of charge. There's a positive charge and a negative charge. A French scientist, his name's Charles Coulomb, he studied charges a long time ago, and he was able to quantify the attraction and the repulsion that two charged particles are going to influence on one another. And this is summarized in what we now call Coulombs Law. And Coulombs Law tells us that the force that's exerted by one charge on another charge is proportional to the product of the two charges. It's inversely proportional to the square of the distance between the two charges, and it will act in a straight line that contains the two charges. So Coulomb's law also states that the force is repulsive if both charges are of a like sign, and the force is attractive if the charges are of a different sign. And additionally, Coulomb was able to experimentally determine that there's a constant of proportionality that relates the force to the charges, and this is 1 divided by 4 pi times the electric permittivity of free space, or of the space that the charges are in, I should say. So if we were to write this out, Coulomb's law, we would say that if we've got two charged particles, Q1 and Q2, the force acting on Q2 by particle Q1 at a distance of R12 is given by F12, the force, it's a vector, meaning it's got a magnitude and a direction, that is equal to Q1, which is just a scalar quantity, times Q2, another scalar quantity. So we multiply the magnitudes of the charge, and we divide that by the constant of proportionality, which is 1 over 4 pi epsilon. If it's free space, it's just epsilon of free space. We then multiply that by the square of the radial distance between them. So that's, if we take the vector between the two of them, we take the magnitude of that vector, that gives us the length of this line here, we square that, and then this force will act in a direction that is in line with the two charges. So we know how to draw a vector pointing from Q1 to Q2, and the force acts in the direction of that vector. And so we'll use the unit vector to represent the direction that that force operates in, a hat, pointing from charge 1 to charge 2. Coulomb was also able to show that the force exerted by multiple charges is calculated by the vector addition of the forces from the other two charges, and this is called the principle of superposition. So let's say that Q3 popped up here. Well, what I would do, I would find F32, which is the force acting on particle 2 from 3. I would draw the vector R32, and it would have a force F32 acting on it, and that would be Q3 times Q2 over 4 pi epsilon magnitude of R32 vector squared a hat 32. And the total force then in this situation is just going to be F12 plus F32. Not B32, F32, excuse me. And this law is called superposition. So Coulombs law can be used for just 2 charges. It can be used for 3 charges. In fact, it can be used for an infinite number of charges. And you just have to add the quantities vectorially, which we described in the last video series. So let's do an example to just kind of get the feeling of using Coulomb's law. And suppose we have a 10 nanocoulomb charge, Q1, and that is located in the Cartesian coordinate system at the location 0, 0, 4 meters. We've got a second charge, Q2. It's 2 nanocoulombs, and it's located at the Cartesian coordinates 0 meters, 4 meters, 0 meters. And then finally we have a 10 nanocoulomb charge, Q3, and it's located in Cartesian space at 0, 0, minus 4. The problem here is, let's determine the force acting on Q2. And I just want to make one kind of elementary physics note about this. In problems like this, clearly, if there are forces acting on charges in space, this would cause the particles to change position, and as soon as the particles change position, the magnitude of the direction of the force is going to change. And so really, in problems like this, what we're doing is we're imagining that the charges somehow are fixed in position. Right? There's like a pin holding them into the fabric of space-time, and they're not free to move. So we kind of got to make that assumption when we're solving these problems. So in reality, you have 2 charged particles, you put them near each other, they're going to push each other apart. Well, what we're doing is we're just calculating the forces that are experienced as if these particles were fixed in position. So I sometimes, when starting problems like this, just like to kind of see what the whole problem statement looks like. And so to do that, I will often plot the particles. So here's an x, y, z coordinate system. And Q1 we see was located at x is 0, y is 0, z is 4. So that's Q1 located on the z-axis. Q2 was located at x equals 0, y equals 4, z equals 0. So that's Q2. And then Q3 is located just along the negative z-axis. So it's like -1, -2, -3, -4. And this doesn't work in all problems, but I like to just get a little bit of intellectual understanding before I solve the problem. Oh, sorry, I should have labeled this. This is Q3. I can see that Q1 is going to act in this direction, and it's going to push Q2 down and to the right. And Q3 is going to act in this direction, and it's going to push the charge Q2 up and to the right. And so if Q1's pushing down and Q3's pushing up, those vector components are going to cancel, or they're at least going to oppose one another. In this case, I can just kind of intuitively tell that they're going to cancel because they're the same magnitude. So what that means is that the vector addition of the force acting by Q1 and Q3 on Q2 is going to point purely in the positive y-axis. And I can tell that just by doing a simple little qualitative analysis of the circuit. I don't know the numbers yet, but I've got a good idea of actually what's happening. And I find that that's often helpful to me when solving electrostatics problems, is to just kind of picture in my mind, well, what do I expect the result to be? And then you can do a sanity check at the end and compare your results of the analysis to what your predictions, your qualitative predictions were, and then compare the two and kind of judge whether or not you think that your answer is at least plausible.